Hello everyone, welcome back. In this video we are going to be talking about the free energy of reaction, and we're kind of going to start into chapter 12.4 and we're going to stick our toe into 12.5, and over the weekend I'm going to get you videos about kind of 12.5 and work to bridge this gap between free energy and where we're going, the equilibrium constant. So this is kind of the start to a much longer, bigger story about the free energy of reactions. So a lot of reactions that we complete in the lab are at constant pressure and temperature. We have a beaker sitting out on the bench. That means that is at constant pressure. And we can stick that beaker into a bucket of water, keeping it at constant pressure, at constant temperature. When we have constant temperature and pressure, spontaneity is best described by Gibbs, the Gibbs Free Energy. And remember that if delta G is less than 0, then things are spontaneous. And we worked through this as we talked about the second law of thermodynamics in terms of mixing and expansion type processes, but now we can extend this into reactions. Now, just like with everything else that we work with, this delta G of reaction is given as the Gibbs of the products minus the Gibbs of the reactants. Or, with some algebra, we can show that delta G at constant temperature is equal to delta H minus T delta S. Now, if you've taken biochem, you should have this this equation burned into your brain. Now, the delta H minus T delta S version of this equation, it really requires either that we assume that delta H and delta S are independent of temperature, which is really only true over small temperature ranges, or we have to have these values of delta H and delta S at or around the temperature that we're interested in. So yes, this reaction is very good for figuring out any temperature and the spontaneity at different temperatures and the temperature dependence of these properties. But we have to make the assumption that delta H doesn't change with temperature, and that's not always the best assumption. Okay, so now let's talk about reactions. Let's take this generic reaction where I have some moles of A reacting with some moles of B to form some moles of Y and some moles of Z. As this reaction goes on, the moles of A are going to decrease and the moles of Y are going to increase. And the moles of A are going to decrease by whatever our initial number of moles of A were, minus the moles times this weird symbol. And this weird symbol is going to be talking about the extent of the reaction. And so early on, we have only changed by a little bit. But at some point, we change by a lot. And this Cauchy symbol is going to really try to say how far along has this reaction gone. And on the product side, we're going to start with our initial moles, and we are going to be adding some number of moles as the reaction progresses. Now, with this reaction progress, we're going to keep using this, and we're going to build on this concept. But and we're going to have to keep this in mind, that during this reaction, what is changing is the number of moles and which species exists. Now, if we go way back to chapter 7, we defined dG as a function of temperature, pressure, and moles. And it gave us this equation of state of dG is equal to minus SDT plus VDP plus mu dN. Now, if we want to find this delta G, we will need to integrate this dG expression. But if we are working at constant temperature and constant pressure, this dT is 0, and this dP is 0. And so what we find is that delta G is equal to this integral of this sum over the mu dNs. And so by using the number of moles determined by the stoichiometry, we can really, and doing that integral, we can find that delta G is really equal to the products minus the reactants. And this can go right into the same concept that we've been working with Hess's law. Because this delta G of formation is something that is tabulated. And so we can think of this as another form of the delta G of reaction being the sum of the products minus the sum of the reactants. Now, we're going to be working, if you notice, in the previous expression, we said that delta G is going to be equal to the sum of VI mu I of our reactants, of our products, minus the sum VI mu I of our reactants. That means that we have to know a little bit about this mu. This mu is the chemical potential. We keep kind of dancing around it. We've been mentioning it for lots of chapters, and we have yet to really figure out what it is. The chemical potential is the molar energy of the sample. And so we can kind of think of this as how many particles exist. The chemical potential is what is used to define the standard state of substances. And it's really how we describe what species exists at what point. And really, these chemical potentials we are going to set as the standard states being our baseline, so that we have some 0 point. And so this delta G is with respect to that 0 point of the standard state. And so if we are thinking about hydrogen, we are talking about H2 gas is its standard state. And so that has a standard chemical potential. But if we took this H2 and we turned it into liquid, we have to do things to this chemical potential to talk about how that species is changing. And so really this chemical potential is trying to identify changes in our species. So, but the real key with chemical potentials, well, for now, we're going to get a lot more abstract and a lot more complicated. But the real key right now is that we have to be very careful comparing thermodynamic quantities from different sources, because different sources can define the standard state of these materials differently. And so if you are looking in one book that is treating H2 gas as the standard state and is reporting something like a delta G for H2 liquid, that would be different than if something was treating H2 solid as the standard state and reporting the value for H2 liquid, because the change between the solid and the liquid is different than the change between the liquid and the gas. And so we really have to be careful about using tables that are from multiple different sources. Okay, so the bottom line is Gibbs Free Energy uses Hess's law. Gibbs Free Energy is also the component, our thermodynamic property, that is really going to start looking at how many moles of what species do we have in the reaction at a given time. And that is going to lead us into these concepts of equilibrium, and we're going to have to keep building on this. And so stay tuned. I've got some more stuff to give you about this section and bridging into the next sections.